Hey, what's up guys?
I've been having an issue tracking my cycling workouts lately. Since I don't have a sensor connected to my bike and fitness app, speed and distance data isn't logged for my biking session. However, I recently noticed I could add my own data, which gave me the idea to create my own cycling tracker. Based off what I had on hand, I decided to make a tracker out of a light sensor and was lucky to have found this video where somebody basically already created what I was going to make. Using the video, I needed some wires, of course a photoresistor, aka the light sensor, a microcontroller, which is basically a little computer we can program to control electronics, a breadboard to power all of our components, an LED to shine at the photoresistor, some regular resistors so we don't burn anything out, and finally a screen to display our cycling data onto. Assembly was quick and the code needed for the circuit to function was provided in the comments, so after uploading the code to the Arduino with some minor tweaks to display a count over time, I had a working prototype. In this little demo, you can see the circuit works by increasing the counter every time the light is blocked from the sensor. To turn this into our biking sensor, I needed a way to block the light in a way that corresponded to the movement of the bike. My bike rests on this trainer that has resistance wheels pressing into the bike rims, so my idea was to make a light blocker driven by the trainer wheels. At first I was planning on replicating this spring-loaded mechanism to press a new wheel with a hole into the existing wheels. This would allow the trainer wheels to spin the new wheel, which would allow light to pass through the hole to the sensor, but block light as the wheel spun. However, I just decided to simplify the whole design and replace the trainer wheel with my own wheel and have the sensor and light mounted around the wheel. The trainer wheel was mounted on the stand with two spacers, allowing the wheel to spin around the mounting screw and keep it from grinding against the stand. Since at its core the wheel was just spinning around the bearing, I took some measurements to design a new wheel with spacers around my own bearing to almost exactly replace the trainer one. Additionally, I made a housing for the electronics to hold the light sensor above the wheel and shine a light from below it, but this was my first time using this specific modeling software, so I was having some difficulties. Once I finished modeling, I started printing on my parts and began some electrical prep work. To start, I didn't want to deal with batteries, so I made a wall adapter for the Arduino using some old power supplies I found at Goodwill. I cut the barrel jack off a 20 volt supply since it was too high but it fit the Arduino, and then I ripped out the 5 volt supply out of an old home phone charger. I soldered both ends together and made some other Cerberus type wires since I didn't have access to a PCB printer, and used what I think is an old lamp cable for the display since I didn't have any long wires on hand. After getting my parts off the print bed, I made sure everything fit and assembled the tracker for testing. Everything powered on just fine, but I quickly ran into some other issues. Firstly, I had to adjust the Arduino's light thresholds since the light and sensor were spaced apart further than in the demo. After that adjustment, I began to get readings, but I ran into the biggest issue of the project, which is that the photoresistor I was using was not responsive enough to catch every time it was exposed to light. If I was moving any faster than like 3 miles per hour, which is nothing, the photoresistor would not read anything.
I'm gonna break my monitor, I swear!
The final issue I experienced was that my plastic wheel slipped a little on the rim, but that was easily fixed just by moving the mount to the tire rubber. While searching if I could even continue this project with a photoresistor, I kept seeing people mention photodiodes were faster and more precise. After more searching, I saw this picture of a photodiode and realized it looked suspiciously like a flame sensor included in my kit, so I replaced the photoresistor in my setup with it. After some more testing and research, I realized my photodiode detected infrared light, so I busted open an old controller, extracted its infrared LED, and changed the blue LED out for the infrared. Finally, I enlisted AI to reduce false positives and help me maximize fast readings.
Response, why don't you ask me later?
What? What?
After beginning the second round of testing, I realized my parts were deforming under friction from spinning. My bearing came loose and the spacers were flattening, which was expected since I wasn't using the strongest filament. To fix these issues, I simply went back to the original wheel and spacers since they were built for the trainer. I drilled a hole into the wheel to mimic my printed one. I also had to cut out some case material holding the IR LED and the photodiode to make room for the wheel. After a final installation, I had to create this abomination of a resistor series since I needed a pull down strong enough to treat the photodiodes like a high to low switch rather than a floating value. The last piece of the circuit required me to calculate what distance I traveled for one rotation of the sensor wheel. From the tire, we can see the larger wheel has a diameter of 24 inches. This larger wheel is driving the smaller one, which was earlier measured to be around 2.4 inches. Since the larger wheel drives the small wheel, we can treat the system like gears. Relating their diameters to get a gear ratio, we get 10:1, which means for every one rotation of the big wheel, we get 10 small wheel rotations. Next, we have to find the circumference of the larger wheel, which is 75.4 inches or 0.0012 miles. Working backwards from the ratio determined earlier, we see the larger wheel only spins 1/10 of its rotation every time the small wheel completes one cycle. So every time we receive a detection, the larger wheel traveled 0.00012 miles. After making the final code update and powering the system on, we can see everything is working great. I zip tied the display cable along the bike frame so it wouldn't get caught in the pedals and we can finally begin pushing our tracker. The speed tracker is great for keeping pace, and the most important part, our distance tracker, can now be used to input whatever distance value is displayed on screen into our fitness app and track our workouts more accurately. A little post-editing note, I never actually checked how much the tracker specific to my watch cost since I assumed it would have been like $100 or something, but this is something I'd probably buy if I biked more.